Hey everyone. As we move from Unit 2 into Unit 3, we're still going to look at this idea of describing motion, but now we're going to start looking at it mathematically. We're going to start looking at quantitatively describing the motion of this object. Whereas opposed to the last chapter where we were talking about describing qualitatively mostly, we talked a little bit about numbers, but this section is going to be much more heavily number focused. Some of you may be happy about that. It's a lot more math. It's, I think maybe in some ways a little bit more intuitive. But those foundations that we laid in the first section, especially with the concepts of position, velocity, acceleration, how they're related, how they cause changes in the other ones, those are things that we're going to stick with the whole year. So it's important that we got those down. I know the test, we'll see about the test. I haven't graded them yet at this point in time when I'm making this video, but you'll get those back on Friday. We'll go over them. I might give you some time to do corrections in class, but then we'll start off with the kinematic equations, start talking about that mathematical aspect, and that's where we're going to end up in this third unit. Lots more problems. We'll talk about gravity a little bit, and that's where we're headed here in Unit 3. Enjoy the video, Introduction to Kinematic Equations, and I will see you soon.
The next section we get into deals with kinematic equations, and like the subtitle says there, motion with uniform acceleration. In the last chapter, we talked about describing motion, and we talked about three things that we want to know, or the last unit I should say, three things that we want to know about the motion: where it is, what it's doing, what it's going to be doing in the future. And we learned that the answers to those questions are displacement or position, depending on if you're talking about now or over a period of time, velocity, and acceleration. Kinematic equations deal with those topics. They are relationships between displacement, velocity, acceleration, and time. But what we find out with our kinematic equations, now that we're getting into the equation part, we're looking at quantitatively analyzing this motion, or looking at numbers, actually making some predictions about how fast is something going to be going at a certain point in time, or how far did it travel within this unit of time if we know some other factors about the motion. Something to keep in mind: kinematic equations only work when the acceleration is uniform, or a constant acceleration. There was a question on the test, Unit 1, asked you about what does it mean when something has a constant acceleration. That means that the velocity is changing at a very regular rate. It keeps getting faster and faster and faster and faster at the same rate, or it keeps getting slower, 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 slower at the same rate. Uniform acceleration means that velocity changes by the same amount during each time period. Okay, now that we know what we're dealing with, like I said, quantitative relationships between displacement, velocity, acceleration, and time, looking at numbers, actually making some predictions about how fast something is going to be going. So let's take a look. There are four equations that we're going to look at here. Okay? I'm going to derive them for you during this presentation, but you are not going to be responsible for the derivations. I just want you to see where these three things, or where these equations come from. And they come from three relationships that we already know about. Here's the first one, right? The definition of velocity, or average velocity: the displacement divided by the time over which that displacement occurs. The second relationship is the one for average acceleration. The change in velocity divided by the change in time over which that velocity change occurs. And then, this one we didn't formally introduce in the last chapter, but another way of calculating the average velocity of something is if we take the final velocity plus the initial velocity and divide that by 2. We did a problem where we looked at something like that, but that was in looking at displacements, and they weren't exactly equal. But if we're just looking at the average velocity, we can add the two velocities, divide them by 2, and get the average, right? That's a math class thing, all right? So let me start here, okay? Final velocity with a constant acceleration. So it says here we start with our definition of average acceleration, delta v over delta t. And to do this, I'm going to get out of here. I'm going to take it over to the notebook, okay? All right, so we start with our definition of average acceleration. A is equal to delta v over delta t. Okay? Hopefully we all remember that when we have delta something, right, we're talking about the change, and in order to calculate the change, we need to know where it ends up and where it started. So we can substitute in V final minus V initial all over T. I'm just going to abbreviate delta T and make it T just to make it a little bit easier to write, but they're the same thing, the time frame over which this occurs. We rearrange this equation, solve for VF, and we end up with VF is equal to VI plus A times T. The final velocity of this object is equal to its initial velocity plus the acceleration times the time, or time multiplied by the time over which that acceleration occurred. And hopefully this makes sense, right? Acceleration tells us the change in the velocity. If we know how long that change in velocity occurs, where it actually started, we should end up with the final velocity. So this is our first kinematic equation. Are they always numbered this way? No, it's just the first one I derive. Okay. So there's our first one. All right. Let me get it out of here, and let's go back here. Something to keep in mind, just like it says right here, this is what we did here. This is probably going to take more time than it's really worth, but that's okay. Some of you will get some benefit out of it, and so I'll do it. Okay. So we started with our average acceleration equation. We rearranged and solved for V final, and we end up with V final equals VI plus A times T. Notice, displacement, one of those descriptors of motion, doesn't show up anywhere in this equation. That's going to be an important theme, so keep that in mind as we go along. All right, let's take a look here. Equation number 2, displacement knowing change in velocity. So the first thing we do, there were 2 equations in that description of or in the previous slide about the 3 equations that we needed to know in order to develop these relationships. And 2 of them were equal to V average, different ways of calculating V average. So what we're going to do is we're going to set them equal to each other, and then solve for delta x, or solve for the displacement. So let me do that here. I'll get out of there, go to my notebook software, start myself a new page. First relationship for V average was V average is equal to delta x over delta t, the displacement that occurs divided by the time frame over which that displacement occurs. That's one of our definitions from the first unit. The second one we said was equal to Vi plus Vf divided by 2. Right? If we know the initial velocity and we know the final velocity, if we just add those 2 together, divide by 2, that gives us the average. These 2 are exactly the same thing. V average, the average velocity, and the average velocity. If we have 2 equations that contain the same variable, we can set them equal to one another. So that's what I'm going to do now. So delta x divided by delta t has to be equal to Vi plus Vf divided by 2. Okay? I do a little math, isolate delta x by itself, and I end up with notice I dropped the delta on the t, same thing, it's just the time frame over which this motion occurs, but I end up with delta x is equal to 1/2 times Vi, the quantity Vi plus Vf, times t. Okay? Second equation that we've looked at. Okay? Let me get out of here, let me go back here. Okay. Once again, probably more trouble than it's worth, or maybe more time than it's worth, but if somebody sees it, and if it helps somebody, I'll do it. Extend the page a little bit here. Edit, paste. There we go. We started with our 2 equations for V average. Those are the black ones up on the top. Then we set them equal to one another because we know they're both equal to V average. Then we solved for delta x. We isolated delta x by itself. We ended up with delta x equals 1/2 times Vi plus Vf over delta t, or times t. Notice acceleration does not appear anywhere in this equation. One of those descriptions of motion that we talked about before, acceleration isn't there. Okay? All right, 2 down, 2 to go. Equation number 3. We're going to start with our first 2 kinematic equations. We're going to substitute the expression for VF from number 1 into equation number 2. They both had VF. And then we're going to isolate, hold on, come on, and simplify and solve for delta x. So another equation solving for delta x, but using some different terms. Once again, I'm not going to hold you responsible for the derivation, but I wanted you to see where it comes from. So let's start off with our first 2 equations. The first equation looked like this. VF is equal to VI plus A times T. The second equation was delta x is equal to 1/2 VI plus VF times T. Okay? So what I'm going to do, notice here's a VF and here's a VF. VF appears in both of these equations. The final velocity of this motion appears in both equations. So I'm going to take this expression and substitute it in here. Okay? All right, so let's go here. Delta x is equal to 1/2 times VI plus, and then I'm going to substitute this whole expression in here, VI plus AT, right, and multiply that all by T. Good so far? I hope so. All right, let's do a little math. Okay, so delta x equals, I'm going to simplify the expression inside the parentheses first. So 1/2 times 2 VI plus AT, multiply the whole quantity by T. Nope, sorry, not T squared, but T. Okay. Then I'm going to distribute out the 1/2 first. Okay. So 1/2 times 2 VI just gives me VI plus 1/2 AT, T still on the outside. Now I'm going to distribute that T through, and I'll end up with delta x equals VIT plus 1/2 AT squared. There's the third equation. Displacement is equal to the initial velocity times the time plus 1/2 acceleration times squared. Notice, because we substituted the expression for VF from the first equation into the expression for VF for the second equation, VF does not appear anywhere in this equation. And just to make that look nice and fancy, all right, you probably can see this even before I move it over, but once again, just in case. Okay. No final velocity anywhere in that equation. Okay. Now, the last expression gets a little bit hairy, and like I said, you are not going to be held responsible for the derivation of this equation, but I just want you to see it so you see where it comes from. Okay, the fourth equation starts with 2 previous equations that we looked at. So VF is equal to VI plus A times T. And then the second expression was the blue one, which was delta x is equal to 1/2 VI plus VF times T. What we're going to do here is we're going to take one of these expressions, I'll take the red one, solve it for t, and then plug t back into this expression here, and I should end up with the same thing on both sides. Or actually what I did was I'm going to rearrange both of these equations for t, and then I'll show you how they set equal to each other. So right now, just watch, see if you follow what I'm doing, and we'll go from there. I rearranged both of these equations, so I got t by themselves, and now, right, because both of these equations are equal to t, I can set them equal to each other, okay? McCabe, I'm sorry about this, but I'm using green. I apologize. Hope you can follow along. So let's start off with VF minus VI over A has to be equal to 2x divided by VI plus VF. And now I'm going to take and I'm going to rearrange this expression and get VF by itself. So once again, you are not responsible for this derivation. You won't have to do it on the test, but I want you to see where it comes from. The math gets a little bit tricky, but we'll see if we can follow it. Okay? First, I'm just going to cross multiply. So VF minus VI times VF plus VI. Yes, I switched the order here, but it's addition. I can do that within the parentheses. And then 2x times A. Okay. Here, do a little FOIL, right? When you do a little FOIL, you end up with yes, it changed the order from 2a to 2x or 2xa to 2ax. Don't ask me why. It's just how we write the equation. Then, all right, VF squared equals VI squared plus 2 times A times delta x. And yeah, I changed x to delta x, but it still represents the displacement. And there is our fourth equation. Hopefully you're picking up on the pattern here and you see that there's some term that's missing in that equation of our descriptions, things we use to describe motion. Because we set these two equations equal to time, or set them equal to time, then set them equal to each other, time does not appear anywhere in this equation. Okay. So those are your four kinematic equations. Let's look at a summary real quick. And let me grab this, go here, okay, bring this here so we can look at it a little bit more. And there it is. Shorten this up just a little bit. There it is. Okay. There's your four equations. I went through the derivations of all four of them. Remember, for about the 15th time, you're not responsible for the derivations. All you're responsible for is knowing the equations. Do you have to have them memorized? Not necessarily. They're going to be up on the wall. They already are. But hopefully, my hope is that the fact that you use them more and more and more, and you'll start to learn them, and you won't have to look up the wall every time. But one important thing to notice, each equation has four terms in it. It has four descriptions of motion, four things we use to describe or measure the motion of an object. But there's always one thing missing. One of those four, or one of those descriptors of motion is missing each time. That means that we can use this equation to make predictions about the motion of an object without knowing everything we can or need to know about that motion. Okay? With that being said, let's wrap this up on this note. Okay? I am not picky about how you solve problems. Okay? I won't mark off if you solve a problem differently than the way we talk about it in class, or if you do your math differently from the way I do my math in class. That doesn't matter to me. But if you're not getting the right answer, I'm going to ask you to follow a certain procedure. And this is the procedure that I always teach. This is how I teach people to go through and solve problems. The first step in solving problems, and when we do work on problems in class, I'm going to ask you this 100 times. First step in the process, what is the question asking for? I make this the first step because you can't make a plan for how to get somewhere unless you know where you're going. Determine what the question is asking for. That should be the first thing that you do. After you do that, now let's list everything that was given to us in the problem. Now we can work with what's there to make up a plan of how we're going to get to what the question was asking for. In this case specifically, when we're talking about kinematic equations, there are 4 variables. There are 4 terms, 4 descriptors of motion in each one of those equations. And that means if we're going to solve for one of them, we got to have 3 of the other, or we got to have the other 3. When we're doing kinematic equation problems, it is important that we find 3 known pieces of information. That's going to then determine which equation we choose to then solve for what we're trying to solve for. That's the next step in the process. Once you know what you're looking for and know what you have to work with, now go to the list, this list, and find out, okay, which equation has the 3 terms that I know and the 1 term that I don't know, so I can solve for that. And the last thing you do, right, solve for the desired quantity. That's the plug and chug part, and make sure we're keeping track of sig digs and all those good things. All right. Just to finish this off, I wanted to give you one example of a problem that we would go through and using kinematic equation and take you through the steps. This is a fairly simple one that I would expect most of you to be able to do on your own. But let's start with the simple ones before we start getting more complex. All right, here's a question from your book. It is actually from, and let me tighten this up a little bit so we're not getting caught on the edges. Okay. This is actually from the 3.3 section review, which is located on page 59 of your book. Okay. Number 1 says, a dragster starting from rest accelerates at 49 meters per second squared. How fast is it going when it has traveled 325 meters? First thing we do, what is this question asking us for? If this says how fast is it going, right, that's asking you for a velocity. And more specifically, it's asking you for a final velocity, right? How fast is it going after it's traveled 325 meters or when it has traveled 325 meters? A lot of the keys to solving these problems is making sure you're reading them and figuring out, okay, what is this question actually asking me for? That's going to be one of the important parts. And then when you decide what it's asking you for, a matter of, okay, what is it giving me to work with? And you'll start learning terminology and learning that keywords mean certain things. So step number 1, what is this question asking us for? Step number 2, what do we have to work with? So it says a dragster starting from rest accelerates at 49 meters per second squared. That's telling us that the acceleration of this object is 49 meters per second squared, right? That's a slap you in the face one. Hey, there it is. How fast is it going when it has traveled 325 meters? 325 meters is a distance, right? It's a length. In that case, that's going to be our displacement, right? That object is going to end up 325 meters away from its starting point. In this case, we can kind of assume that it's positive, and that's okay in this case. For the acceleration, because this object is going faster, faster, faster in the same direction that it's moving, we're going to call that a positive acceleration as well. Now, like I said, important thing sometimes is reading the problem and deciphering what it's actually asking you for. If this says a dragster starting from rest, right, without telling you, that's giving you a piece of information. That's telling you that the initial velocity is equal to 0. If it says it starts from rest, that means, okay, it started and it wasn't moving, so its initial velocity is equal to 0. What are we looking for? What do we know? Next step in the process is pick the appropriate equation. So if we head back to our list, right, we knew that we were looking for V final. That's the one thing we were trying to find out. We knew we had the initial velocity. It gave us the acceleration, and it told us how far this object had gone. it made no mention of the time, but remember there's one equation out there that doesn't have time in it. So you use this chart, or you just look at the equations, and you see that this equation down here at the bottom, there's no mention of the time. But it has v final, it has v initial, it has acceleration, and it has displacement. We know the initial, we know the acceleration, and we know the displacement, and we're trying to solve the final velocity. It's important that the equation you choose has the variable that you're trying to solve for. That way you can actually solve for it. Move ahead, right, back to our problem, and we saw from our list that vf squared equals vi squared plus 2 times a times delta x has all of the information that we need, and then we can, or information we have to work with, but also the variable that we need to solve for, so we can do that. So I'm just going to do that real quick. If you want to hit pause and do it on your own, that might be a good idea, but if not, you can just watch. A lot of times when I'm working through problems as examples, I won't carry my units necessarily, so don't be alarmed if I'm doing that. And then do some math, and we end up with, okay, a couple of things here. First, I just wrote down like the first, whatever that was, 8 numbers that my calculator gave me. Second, when I do a square root to solve this problem, I actually get 2 answers, right? A plus and a minus. Mathematically, there are 2 answers to this question, but physically, there's only one answer that makes sense. If I started with a 0 velocity and I called my acceleration positive, that means I'm speeding up from rest. Which direction am I speeding up? The positive direction. So while mathematically there are 2 answers to this question, my answer has to be the positive answer, because that's which way I'm going. Remember, those positive and negative signs. We're using math to help us model the motion of this object. But physically, those positive and negative signs tell us something about that motion. So while mathematically there are 2 answers to this question, there's only one answer that makes sense physically. Then, if we start looking at sig digs, right, 2 sig digs in the acceleration, 3 sig digs in the displacement, and while I wrote down that vi is equal to 0, it's really exactly 0. So it's like 0.00000 blah, 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 and there's no sig digs or that's infinitely significant. So I need to round my answer to 2 significant digits. So there's my answer. Hope this worked for you. In class, we'll do a lot more problems. There is really no more conceptual things we have to talk about in terms of solving these kinematic equation problems. Lots of practice in class. Then we'll start talking about some applications where the kinematic equation process works for us physically to model a situation that we deal with all the time. More in class.